Every photon that strikes your retina on a clear night has been traveling, some of it for thousands of years, some for billions, crossing an unimaginable void to die quietly against the back of your eye. You are not seeing the universe as it is. You are seeing a ghost of it, a fossil record of light, ancient and incomplete, and the universe has been very deliberate about what it chooses to show you. Because there are barriers, two of them, vast and patient. The first is cosmic dust, colossal curtains of gas and particulate matter that swirl between star systems and entire galaxies, concealing the regions behind them as effectively as a wall of stone. Behind those curtains, things are being born, stars, planets, entire solar systems collapsing out of nothing. And we have never seen them, not clearly, not truly. The second barrier is subtler and in many ways more profound. Space itself is expanding, stretching outward in every direction simultaneously, and as it stretches, it pulls light along with it. Light from the most distant objects in the universe, having traveled so far and for so long, finds its wavelength elongated beyond the visible spectrum entirely. It becomes infrared, heat radiation, invisible to the human eye, invisible to every instrument we had built until very recently. For centuries, these two barriers conspired to keep the universe's deepest secrets locked away. We had never seen the first galaxies, the original structures that formed when the cosmos was barely an infant. We had never witnessed the precise, violent moments when stars ignite for the first time. The origin story of everything had remained, stubbornly, just out of reach. Then, on Christmas morning, 2021, a rocket climbed above the atmosphere and released something extraordinary into the void. The James Webb Space Telescope, a machine that took 30 years to conceive and build. A $10 billion collaboration between three space agencies, NASA, ESA, and the Canadian Space Agency, representing perhaps the most technically complex object ever manufactured by human hands. Its primary mirror alone spans 6.5 meters, composed of 18 gold-coated beryllium hexagons that had to unfurl with millimeter precision in the cold of deep space. Its sunshield, the size of a tennis court, had to deploy like origami in the dark, protecting instruments that operate just barely above absolute zero. It was designed to be a golden eye. And it has seen things that have shaken the foundations of what we thought we knew. As of 2025, the James Webb Space Telescope has completed more than 860 scientific programs and accumulated nearly 550 terabytes of data, more than Hubble gathered across its entire 35-year operational history. But these are not simply photographs. They are measurements, evidence, and some of what that evidence suggests has sent tremors through the entire field of cosmology. This is the story of what James Webb has found, and what it may mean. Before we travel to the edge of time, we begin closer to home, in our own solar system, because even here, this instrument has a way of making the familiar, suddenly, profoundly alien. Neptune, the eighth planet, the outermost giant. In visible light, it is a deep, saturated blue, methane in its upper atmosphere scattering sunlight into that distinctive hue. Easily recognizable, comfortably known. Webb does not see it that way. Through Webb's infrared instruments, Neptune is almost dark. The same methane that creates its blue appearance absorbs infrared radiation almost completely, leaving very little for the telescope to detect. The planet itself becomes a kind of absence, a void in the shape of a world. But that darkness is not empty. It is revealing. Without the overwhelming glow of the planet's body drowning out subtler signals, Webb's sensors pick up what was previously too faint to see clearly. A ring system of breathtaking delicacy. Dusty, narrow rings that orbit Neptune in almost perfect silence, visible now in crisp, dramatic relief against the blackness of space. Not the solid, obvious rings of Saturn. These are gossamer structures, barely there, like smoke rings frozen in place around a dark sphere. The images are the clearest ever taken of Neptune's ring system. They have also revealed previously unknown arc structures within those rings and confirmed the positions of 14 of the ice giant's known moons, tiny points of light orbiting in the cold at the edge of our solar neighborhood. Scientists are still working through the data. There are almost certainly more discoveries hidden in those observations. But Neptune, for all its strangeness, is a neighbor. Something far more unsettling arrived in the inner solar system just as Webb was beginning its operations. And it did not come from here. On the 6th of August, 2025, Webb turned its near-infrared spectrograph toward a comet. Not an ordinary comet, an interloper. Designated 3 the Panxiao Atlas, this object had been identified as interstellar in origin, meaning it had not formed in our solar system at all. It had traveled from somewhere else, from around some other star, and was now passing through our neighborhood on a trajectory that would carry it out again into the dark between the stars. A messenger, a visitor that would never return. What Webb found when it analyzed this object was, to put it simply, a Pandora's box. The comet was extraordinarily rich in carbon dioxide and water vapor. The ratio of these compounds was among the highest ever measured in any comet, solar or interstellar. This was not what most models had predicted for an object from another star system. The implications are significant. The presence of these specific molecules, HCO2 ice forming only where temperatures drop low enough in a planetary disk, tells us something about where this object was born. It formed in the cold outer regions of another star's planetary disk in conditions that mirror the regions of our own solar system where the giant planets condensed. Which means the basic chemical inventory that gave rise to our world, water, carbon compounds, the raw materials of life, is not unique to us. It is universal. The processes that built our solar system are not a local accident. They are a standard feature of the galaxy. And somewhere out there, around the star that 3I Atlas once called home, those same processes were at work. The same molecules, the same conditions, the same potential. Webb has proven it directly for the first time by reading the light of something that traveled between stars. For decades, astronomers have suspected that planets orbit Alpha Centauri A and Alpha Centauri B, the 2 sun-like stars at the heart of our closest stellar system, just over 4 light-years away. The problem has always been the same. The binary pair is so bright, their combined glare so overwhelming, that any planets around them have been effectively invisible, hidden in plain sight by the very stars they orbit. Webb has now bypassed this problem. Using its mid-infrared instrument and an internal coronagraph, a device that functions like a visor, blocking the intense starlight while preserving the faint signals around it, Webb has detected what appears to be a planet, the closest exoplanet candidate ever to be directly imaged, a world in our backyard that has always been there, waiting to be seen. The signal corresponds to a Saturn mass gas giant. And here is where things become more interesting and more unsettling. Orbital simulations based on the detected signal suggest this world may follow an elliptical path through the habitable zone of Alpha Centauri A, the region around a star where liquid water could theoretically exist on the surface of a solid world. The gas giant itself is not a candidate for life as we understand it, but its presence raises a question that is difficult to set aside quietly. If a gas giant has formed in this system, other worlds may have formed too. Smaller ones, rockier ones, worlds that Webb has not yet detected. We are looking at a planetary system right next door that has been there all along, one that we have only just managed to glimpse for the first time. To understand how planets form, we must first understand how stars are born. And to understand that, we must go inside the clouds of gas and dust where it happens, places that, until Webb, were opaque to observation. The pillars of creation, the cosmic cliffs of the Carina Nebula. These structures were photographed by Hubble and became iconic images, monuments of cosmic architecture. But Hubble's visible light instruments could not penetrate the dense, dusty columns. The nurseries within were sealed. Webb's infrared instruments pierced them like a scalpel through fog. In Webb's near-infrared images of the pillars of creation, thousands of previously unseen stars have emerged. Among them, something stranger, newborn stars, still encased in their cocoons of dust, glowing red at the edges of the dark columns. These objects are estimated to be only a few 100,000 years old. In cosmic terms, they were born yesterday. And they are not quiet. Energetic jets of plasma blast outward from these infant stars. Shock waves pulse through the surrounding material. The tips of the pillars seem to throb with activity, a violence of creation that Hubble's images could not reveal because the evidence was hidden in wavelengths it could not see. The cosmic cliffs tell a similar story. Webb's sharp infrared vision has revealed the fine detail of turbulent gaseous structures at the edge of the nebula, being sculpted and eroded in real time by the radiation pouring out of massive young stars nearby. The nebula is not static. It is being destroyed and rebuilt simultaneously, a process that has been underway for millions of years and will continue long after our sun burns out. But it is in the far outskirts of the Milky Way, in a region called Sharpless 2-284, some 15,000 light-years away, where Webb has found something that reframes our understanding of stellar birth entirely. Embedded in a sparse cluster of young stars at the galaxy's edge, Webb's infrared eye has resolved a protostar unlike anything observed in such detail before. A single stellar embryo weighing as much as 10 times the mass of our Sun. It is not forming quietly. From its poles, twin jets of superheated plasma are erupting outward, a bipolar outflow of extraordinary scale. The jets span 8 light-years. To put that in perspective, the entire distance from our Sun to Alpha Centauri is just over 4 light-years. These jets are nearly twice that length, blasting through the surrounding molecular cloud and excavating 2 enormous opposing lobes of gas. This is what astronomers call a Herbig-Haro object, the visible signature of a stellar birth announcement created when outflow jets plow into surrounding material and heat it to luminescence. Over 300 Herbig-Haro objects have been catalogued. But this one is different. Its scale, the symmetry of its outflow, the stability of the jets. All of this points to an unusual degree of order in what is typically a chaotic process. The structure suggests the star is forming through an organized accretion disk, providing evidence for the core accretion model of massive star formation. And then there is the environment. This protostar sits at the extreme outer edge of the Milky Way, in a region of extremely low metallicity, meaning the material available to it contains very few heavy elements, almost entirely hydrogen and helium. No carbon, no oxygen, no iron to speak of. This pristine primordial composition is not found in the inner galaxy, but it is, in essence, what the early universe looked like, before generations of stars had lived and died and seeded space with heavier elements. In studying this protostar's birth, Webb may be giving us a controlled experiment, a glimpse of how the very first stars formed in the earliest epochs of the cosmos, when there was nothing but hydrogen and gravity and time. The implications, if confirmed, are profound. The story of planetary formation does not end with the star. Once the chaos of birth subsides, the remaining material organizes, a swirling disk of gas and dust that gradually assembles into worlds. And sometimes those worlds have their own disks. In the CT-CHA-B system, 625 light-years away, Webb has delivered the first direct chemical measurements of a circumplanetary disk, a structure surrounding a young, massive exoplanet believed to be a formation site for moons. A miniature solar system within a solar system. We believe our own moon system around Jupiter formed through exactly this process, billions of years ago. CT-CHA-B allows us to watch it happening now. What Webb's instruments detected in that disk is unexpected. The disk surrounding the planet is rich in complex organic carbon compounds, acetylene, benzene, the raw ingredients of organic chemistry. But the disk surrounding the host star, just next door in cosmic terms, is different. Water, but almost no carbon. Two disks in the same young system with radically different chemical compositions. The system is only about 2 million years old. It is already diverging, already producing different chemical environments that could, in theory, lead to very different kinds of worlds. The contrast with our own solar system, where rocky, carbon-poor inner worlds orbit alongside gas giants with carbon-rich moon systems, may not be coincidence. We may be watching in real time the same differentiation that shaped our own planetary neighborhood 4 billion years ago. In 2024, Webb turned its attention to 19 nearby spiral galaxies and returned images of such startling beauty that the line between scientific observation and art seems to dissolve entirely. But these are not merely beautiful pictures. In the Phantom Galaxy, NNGC 628, 32 million light-years away, Webb's instruments do something that Hubble could not. They separate the components of the galaxy into distinct layers of meaning. Blue light marks the concentrated mass of older stars in the galactic core. Red and orange paint the threads of dust and gas spiraling through the arms, the raw material of ongoing star formation. Bright points of deepest red mark stars still encased in their birth clouds, not yet visible in any other wavelength. And then there are the voids, giant spherical shells carved into the spiral arms by ancient explosions, supernovae that detonated millions of years ago and whose shock waves are still propagating outward through the galaxy, compressing gas ahead of them and triggering new waves of star formation even as they clear space behind them. Across 19 galaxies, these same patterns repeat. The same processes, the same structures, the same cycles of death triggering birth over and over at every scale. It is a portrait of how galaxies breathe. All of this, Neptune's rings, the interstellar comet, the nearest exoplanet, the stellar nurseries, the protostar at the galaxy's edge, the moon-forming worlds, the spiral galaxies. All of it has been prologue. Because the question that drove the construction of this instrument, the question that motivated 30 years of engineering and $10 billion of investment, was more fundamental than any of these discoveries. More unsettling. It was this: what did the universe look like when it first began making things? To answer it, Webb must look not just far, but to the very edge of the observable universe, to a time only 300 million years after the Big Bang, when the first structures were emerging from the primordial dark. Even light has limits. The very earliest radiation in the universe, released when space first became transparent a few 100,000 years after the Big Bang, marks the observational horizon. Beyond it, there is no light to catch. But physics offers a tool for seeing farther: gravitational lensing. When Webb observes massive galaxy clusters, their gravity warps the fabric of space-time around them. This warping acts as a natural telescope, bending and amplifying the light from objects behind the cluster, objects billions of light-years more distant. In 2023, Webb observed a galaxy cluster called RxJ 2129, located 3.2 billion light-years away, and detected a supernova explosion behind it, not once, but multiple times. The same explosion seen as 3 separate echoes because its light had taken 3 different paths around the cluster, each of different lengths, arriving at Webb at measurably different times. By analyzing these time delays, astronomers can precisely calibrate cosmic distances and refine our measurement of the rate at which the universe is expanding. This value, known as the Hubble constant, has been the subject of significant disagreement in recent years. Webb may have the precision needed to resolve it. But it is what Webb has found at the very edge of its vision, at the furthest distances it can probe, that has sent the deepest tremors through the scientific community. In the depths of the JD's survey, one of Webb's deepest infrared observation programs, something appeared that the models said should not be there. A galaxy. Designated JADES-GS-Z14-0. Its light, stretched by the expansion of space into the infrared, corresponds to a redshift of 14.32, meaning We are seeing it as it existed only 300 million years after the Big Bang. Among the earliest confirmed galaxies in the observable universe, it should be small, dim, just beginning to coalesce. The prevailing lambda cold dark matter cosmological model, the standard model of cosmology, refined over decades of observation, predicts that galaxies at this epoch should be primitive structures, barely distinguishable from the clouds of gas that preceded them. JADES-GS-Z14-0 is not that. It is already large, already luminous, already showing signs of significant stellar mass. A galaxy that, by all standard models, should not have had enough time to become what it appears to be. It is not alone. Several similar objects have now been identified, a pattern that is becoming impossible to dismiss as measurement error or statistical noise. The models are failing, not marginally. The discrepancy between what the standard model predicts and what Webb is actually observing is large enough that astronomers are now openly discussing the possibility that our fundamental understanding of how structure forms in the early universe requires revision. One hypothesis that has returned to serious discussion is deeply strange. In 2007, cosmologists Catherine Fries, Paolo Gondolo, and Douglas Spolyar proposed the theoretical existence of what they called dark stars. Hypothetical objects that would have formed in the very earliest universe, powered not by nuclear fusion, as all ordinary stars are, but by the gravitational annihilation of dark matter particles within their cores. Dark matter, which we know constitutes most of the universe's mass, but which we have never directly detected, would heat these objects from within, allowing them to grow to extraordinary sizes, potentially millions of times the mass of our Sun, before collapsing. These objects would be cool, bright in infrared light, and long-lived. Exactly the kind of signature Webb's instruments are designed to detect. The existence of dark stars, if they existed, could explain why the earliest galaxies appear so much more developed than our models allow. They could have been the seeds, the heavy progenitors that allowed structures to grow faster and larger than ordinary stellar physics permits. We do not yet know if this is the answer. We do not know if dark stars are real. But we are looking at galaxies that should not exist. And the instrument that found them is still operating, still collecting data, still peering into wavelengths and distances that no instrument before it could reach.